Hello everyone. Today, let's talk about curvature. First, let's review what it means a single variable vector function. A single variable vector function R takes one variable, usually t, and returns a vector R of t. We are interested in mostly for R of t being a three-dimensional vector. Now, we have this new definition. Parametrization R of t is called smooth on an interval I if R prime is continuous and R prime of t never equal to 0 on that interval I. Now let's look at this parametrization R of t that's equal to t squared I plus tqj plus t to the 4 k. Notice that R prime of t is equal to 2ti plus 3t squared j plus 4tqk. Each component function is continuous on all real number. So R prime of t is continuous. So satisfy this condition. Notice that R prime of t is equal to 0 even only if t is equal to 0. So R prime of t equal to 0 here. So it doesn't satisfy this second condition. So this R of t is going to be not smooth on any interval that containing 0. For example, from -1 to 1, it contains 0. R of t is not smooth. However, if you choose the interval to be from 1 to 2, then R prime of t is never going to be 0 on 1 to 2, then R of t is going to be smooth. Geometrically, let's try to visualize this. So a curve is called smooth if it has a smooth parametrization. A smooth curve has no sharp corners or cusp. And when the tangent vector turns, it does so continuously. So here is a smooth curve. So imagine that the t here is on this interval I, and then this vector function R is going to map this into a space curve. Now, what does this one here means that R prime is continuous? That means the rate of change of this R, this position vector R, is going to be continuous. And R prime of t does not equal 0 on this I. That means on this curve over here, which is the image of this I under this vector function, the rate of change of this R is never going to be 0. So the rate of change doesn't equal 0. That means the position will keep on changing. It's not going to just stay there. The rate of change is never going to be 0. So if you're looking at the space curve over here, then this curve is smooth. Basically, we should have no sharp corners or cusps. Okay, so very nice smooth. And when the tangent vector turns, it does so continuously. So remember, the tangent vector corresponds to R prime. So it should be continuous. So when the tangent vector turns, it does so continuously. So here's an example of a smooth curve. Now let's go back to this example in the beginning. So R of t equal to t squared I plus tq j plus t to the 4 k. Let's graph this. And you see that the graph of this vector function is going to be smooth, a very nice smooth, except at when t equal to 0. See, you can see from different angle. You see the curve is going to be smooth, no cuts, no corner, and the tangent line will turn continuously. However, when t equals 0, and what happened here? There is a cusp, there's a corner over here. So you see that the curve for this vector function is going to be smooth everywhere except when t equals 0. So if you choose an interval that doesn't contain 0, the curve will be smooth curve. And if the interval contains 0, let's say from -1 to 1, and then you see that at t equals 0, you have a corner here, and it's not a smooth curve. So for you guys to remember, just remember a smooth curve has no sharp corner or cusp. And when the tangent vector turns, it does so continuously. Now, if C, and let's call this curve C here, and if it is a smooth curve defined by the vector function R, we call that the unit tangent vector T of t is given by, anyone remember what does it equal to? That's equal to the tangent vector at this point divided by the magnitude of that tangent vector. And that's called the unit tangent vector. And what does this unit tangent vector do? It indicates the direction of the curve. So at this point, you have this direction of the curve, and then it changes direction like this, right? So the unit tangent vector indicate the direction of the curve. See all those pink vector there is the unit tangent vector of the curve. And let's look at this figure. You can see that the unit tangent vector T of t changes direction very slowly when the curve is kind of straight, very straight. Like over here, it's kind of straight, right? So the direction change is kind of slow, okay, like that. So the more straight the curve, then the unit tangent vector is going to change slowly. Now, when it changes direction more quickly, for example, from here to here, the direction, okay, actually from here to here, the direction here change more quickly. And you can see that the curve C bends or twists more sharply, right? Do you see that? It bends and twists more sharply. The direction of the tangent vector change direction more quickly when the curve bends or twists more sharply. So try to imagine this is the charging wire of your cell phone, okay, like that. And you bend it over here, then the direction over here, the unit tangent vector here change quickly over here, and the curve over here bends or twists. So when the curve here bends or twists, like here, then the unit tangent change direction quickly. The curvature of that curve at a given point is a measure of how quickly the curve change direction at that point. So if you want to measure how quickly the curve change direction, we will use something called curvature. And we define that to be the magnitude of the rate of change of the unit tangent vector with respect to arc length. So the notation for curvature is kind of like a K, a fancy K, and it is going to be the magnitude. So we put the absolute value here. That means that This one here stands for the magnitude. And this one dt here is, remember t is the unit tangent vector. Now dt ds, s here is the arc length. So that is the rate of change of the unit tangent vector with respect to the arc length. And then you take the magnitude of this. That's called the curvature. Now remember, the unit tangent vector has length to be 1. So the length of that, it doesn't contribute to this rate of change here. So the only the change in the direction of the unit tangent vector is going to contribute to this rate of change over here. So look at this one, look at this curve. Let's try to understand curvature by looking at this curve here. You see, those points on this curve are evenly spaced. And between them, the arc length will be, let's just say, will be 1, each one of them. And then here are the unit tangent vector, and all of them has length to be 1. Unit tangent vector has magnitude to be 1. Now dt ds. So we want to see the rate of change of this unit tangent vector with respect to the arc length. Then only the direction change of the unit tangent vector is going to contribute to this rate of change. So you see the direction here change this from this direction to this direction, and then to this direction, etc. Right? And you see that the direction change over here, you see here, the curve is kind of straight. Okay, so the direction here doesn't change quickly. However, you see the curve over here, it bends right here, and the direction of the unit tangent here change more rapidly. So this part here has bigger curvature. This part here has smaller curvature. So curvature actually measure how quickly that the curve change direction. So the quicker this curve change direction here, the bigger the curvature. See here we have bigger curvature, here has bigger curvature, but here is more straight and the curvature will be smaller. Now the curvature is easier to compute if it is expressed in terms of the parameter t, okay, instead of the arc length s. We can use the chain rule to write this. So the rate of change of big T, which is the unit tangent vector, with respect to t, this variable t, this independent variable t, the parameter t, is going to be dt ds times ds dt. Now remember the definition for curvature is the magnitude of dt ds. Now dt ds over here is going to be dt dt, d big T, d small t, and then divide by ds dt. So we replace this by that, we get that's equal to the magnitude of this. Now pay attention, the big T here is the unit tangent vector. The s here is the arc length. The small t over here is the parameter, and usually is the time. Now remember ds dt. What's ds dt? The rate of change of the arc length with respect to the parameter t. Now remember when we talk about arc length function last time, we had the arc length function is equal to this integral right here, and we use the fundamental theorem of calculus part 1. When we differentiate this function with respect to t, we get back this function that we integrate with, except this time the variable here will be t. So we have ds dt is the magnitude of r prime of t. Now we can replace this ds dt. It's going to be the magnitude of r prime of t. So this is r prime of t, and dt dt is the rate of change of the unit tangent vector with respect to t. Usually t is the time. Then this will be the magnitude of t prime of t. That's t prime of t up here. Down here, it is the magnitude of r prime of t. So we got this formula over here. And here is a picture to show that what's the unit tangent vector. So each one of this is a unit tangent vector. And you just take the tangent vector and divide by its magnitude. Then you get those unit tangent vector at each point on the curve. So let's write this one more time. The curvature is equal to the magnitude of t prime of t divided by the magnitude of r prime of t. Now let's try to get a little bit more comfortable with curvature by looking at this example. In this example, we try to show that the curvature of a circle of radius a is 1 over a. So here is a circle and the radius is a, and we try to show that the curvature is equal to 1 over a. Remember, curvature measure how quickly the curve changes direction at each point, right? So once you see along this circle, how quickly the curve is going to change direction. According to this, looks like the way that it changes direction is 1 over a. But let's find out. First, we can take the circle to have center at the origin to make our parameterization a little bit simpler. Well, if we want t to be this center angle over here, notice that x-coordinate of this point is a cosine t, y-coordinate of this point is a sine t, then r of t will be equal to a cosine ti plus a sine tj. So that is a parameterization of this curve using t here as the center angle. Now we're going to, in order to calculate the curvature, we're going to find r prime of t first. To find r prime of t, we're going to differentiate each component function. So differentiate a cosine t, we get negative a sine t. Differentiate a sine t, we get a cosine t. Now we're going to calculate the magnitude of r prime of t. The magnitude of this r prime of t, that's equal to the square root of the square of this component plus the square of this component. So at the end, we'll get a. The magnitude of that is a. Now, next, we need to find t prime of t. But in order to do that, we need to first find t of t first, and then later differentiate to get t prime. Now, t of t, remember, that's the unit tangent vector. T of t is the unit tangent vector. So we'll take the tangent vector, divide by the magnitude of tangent vector. So r prime of t we already got here. And then we just divide that by its magnitude, which is a. So divide this by a. The a here cancel. So we get negative sine t I plus cosine tj. Now we are going to differentiate because we want to get t prime. So differentiate this with respect to t. The derivative negative sine t is negative cosine t. The derivative of cosine t is negative sine t. Now we're going to find the magnitude of t prime. And square this plus the square of this, we will get 1. And take the square root, we also get 1. So the magnitude of t prime of t is going to be 1. Now using this formula for curvature, so the magnitude of t prime here is 1. The magnitude of r prime here is a. So the curvature is 1 over a. Now what does this say? That says that if the circle has radius a, then the curvature, which measures how quickly that the curve change direction, is going to be 1 over a. So for example, if the radius of the circle is 2, then the curvature of this curve will be 1/2. When the radius of the circle is 3, the curvature of this circle is 1/3. Well, which makes sense. When you have a circle has smaller radius here, the curvature is actually bigger than the circle has larger radius. This one here, the curve changed direction more quickly. And remember, only change in direction contribute to this curvature. So that makes sense. The bigger the radius, the smaller the curvature for circle. And it's related curvature of a circle. Now you can repeat after me. The curvature of a circle with radius A is going to be 1 over A. And that's a result that is worth remembering. So what's the definition of curvature? This is the definition of a curvature. We see that from this definition, the curvature of a straight line is always 0. Why? Because the unit tangent vector doesn't change direction along a straight line. So imagine if you have a straight line over here, then the unit tangent vector doesn't change direction. So the rate of change of the unit tangent vector with respect to the arc length is going to be 0. So curvature of a straight line is always 0. Now, although this formula here can be used in all cases to compute the curvature, the formula given by this following theme over here is often more convenient to apply. And what does it say? It says that the curvature of the curve given by the vector function r is going to be the magnitude of the cross product of r prime with r double prime, and then divide by the magnitude of r prime and raised to the third power. Now, this one here, for the proof of this theme, please refer to your textbook. Now, let's consider a special case. We have a curve on a plane. So the one we have over here, this one here is for curve in 3D. Now, let's just consider the special case when the curve is on a plane. It's a 2D curve. And let's say the equation of this curve is y equal to f of x. We can choose x as the parameter and then y r of x to be, well, you see that the x component of this position vector will be x. And then the y component, you can express it as f of x. So r of x is x in the I component, and then it will be f of x in the j component. So we can parameterize it this way, using x as the parameter. Now, what's r prime of x? Differentiating this, we get differentiate x, we get 1. Differentiate f of x, we get f prime of x. And let's find r double prime. So differentiate this one more time. The derivative this is a constant vector. So the derivative of I will be 0. And then differentiate f prime, you get f double prime of x. So we got this. Now, we're trying to use this to calculate the curvature. Remember, this is curvature for 3D space curve. So we need to find the cross product of r prime with r double prime. I cos j, what's I cos j? I cos j is, use the right-hand rule. I cos j will be k. And j cos j, any vector that cos itself will be equal to 0. Remember, when you use this vector, cos this vector, we can actually distribute, remember? So we have I cos this, and because I cos j is k, so we get f double prime of x k. Now, and then what happened to this? Cos this. This one cos this, because j cos j is going to be the 0 vector, so we get 0 when you use this cos this. So the result here will be f double prime of x in the k direction. You can also do it this way. So when you expand this, so the I component will be 0, z component will be 0 also. And then the k component will be f double prime of x. So you got this result here. Now what else we need? We also need the magnitude of r prime. The magnitude r prime over here, let's take the magnitude here. There'll be 1 plus the square of f prime. And then we're going to take the square root of that. So that is to the 1/2 power. But then this formula here says that we're going to raise that magnitude to the 3rd power. So that's why here is 3 over 2 power here. Now we got this new formula here. This is a curvature, especially for plane curve, which means it's a curve on a 2-dimensional plane. And what's the difference between this one and this one? This is the general formula. This is for 3D space curve. And this one over here is for 2D plane curve. So pay attention. 2D curve for this, and this one here for 3D space curve. Now I have a side note for you. Remember, for a 2D plane curve, the arc length is this formula. Okay. Now for 2D plane curve, the curvature is given by this formula. So you can put them together. Remember this. Now let's try to use this formula in this example. Find the curvature of the parabola y equal x squared at the point 0, 0, 1, 1, and 2, 4. Notice that this parabola is on the xy plane. It's a plane curve, y equal to f of x. So we can calculate the curvature, use this formula. So we first calculate the duality, and then later calculate the second duality. The duality of that is 2x, second duality is 2. Now we're going to put that into this formula. The magnitude of y double prime is 2, and y prime is 2x. So this square of that will be 4x squared. So the curvature of this curve, this parabola, okay, is going to be equal to this. Now, we want to find the curvature at 0, 0, 1, 1, and 2, 4. All we have to do is substitute the different x value into this. So calculating, we get the curvature at 0 is 2, at 1, 1 is about 0.18, at 2, 4 is about 0.03. Now, if you're looking at the curve, and you can see that the curvature at 0 here is equal to 2, and now at 1, 1, the curvature is about 0.18, and at 2, 4, the curvature is about 0.03, so it gets smaller. So what have we learned today? Today we learned about curvature. This fancy K here is the rotation. That's equal to the magnitude of the rate of change of the unit tangent vector t with respect to the arc length. The second formula that we learned about is the curvature at t is given by this quotient, which is the magnitude of t prime, divided by the magnitude of r prime. C, what do we learn here? For all space curve, says that the curvature at, say, time t, that's equal to the magnitude of the cross product of r prime with r double prime at t, and then divide by the magnitude of r prime raised to the 3rd power. And this is for all space curve, so including 2D and 3D. Now, the last part we learned is the curvature is equal to this. Now, notice that this formula over here only applies to 2D plane curve. When y is a function of x, you can use this formula to calculate the curvature. And that's what we learned today.